Hey all, welcome everyone to this webinar on the case for open source, how k0rdent empowers enterprise agility. As you all know, k0rdent, a newly launched project on distributed container management. We'll be talking a lot about it, and we'll introduce k0rdent. We'll talk about platform engineering practices, but just introducing the webinar to you all. My name is Prithvi Raj, and with me is Bharath. We'll quickly introduce ourselves. I started my journey as a community manager for Maya Data, and then I started off with the Litmus Chaos open source project, which is a CNCF incubating project on chaos engineering. 4 years down the line, I joined Mirantis after this journey from chaos native to harness, and now at Mirantis, where I'm actively contributing to the k0s and k0rdent projects. I also am actively involved in the community where I run the Kubernetes Community Days Bangalore. I started off with the CNCF Reliability Engineering Meetups and Litmus Chaos Con and Chaos Carnival as well, which is a global conference. And now I'm actively focused on projects developed by Mirantis, actively sponsored by Mirantis, and obviously helping the open source program of his community activities at Mirantis. And you can connect with me on these socials. Bharat, would you like to go next?
Hey, thanks, Prithvi. Hey guys, I'm Bharath. I'm a open source contributor and a senior software engineer at Mirantis. I've joined Mirantis last year with the OSPO team. I've always been a huge supporter of open source technology. Before this, I've worked at companies like Red Hat and Hewlett Packard, where um, I've worked on things around Kubernetes for a while now. It's been a good journey. Mirantis, the focus here has been more towards k0rdent, which we're going to talk about today, and how we can shape the open source community in this particular segment of it.
So, moving ahead, what's on the agenda today? I mean, there are so many things that we'll discuss, but I just wanted to put forward a few points. We'll obviously discuss how did we introduce this project, k0rdent, the challenges which platform engineering today provides. I mean, platform engineering is a term a lot of folks might have heard, are still new to it, and then obviously the challenges it provides, and then how the project k0rdent came into place. Bharat will be talking about the architecture and the overall overview, and obviously will demo k0rdent for us and help us get started with k0rdent as a community. And then obviously we'll take some Q&A if that's there, and we'll wrap up. As you know, when cloud computing first emerged, say around 20-25 years ago, the promise was simple: just consume infrastructure as a service and everything would be easy. But if you talk about today, I mean, today it's so different. I mean, what customers expected was a simplistic overview of just interacting with your data centers or with code. But with so many cloud providers, I mean, you have got GCP, you've got Azure, you've got AWS, you've got, I mean, your private cloud, your hybrid cloud environments. There is a battle for control. I mean, between proprietary softwares, your public clouds, data centers, providers, your APIs, and infrastructure. And it has created a large level of complexity for all organizations. I mean, each and every organization that we talk to, as a community manager, I have talked to, are struggling to navigate through this. They want to maybe move on to one cloud provider, maybe have just differentiating private clouds, public clouds, that is it. But you know Kubernetes came in as a solution to solve this. I mean, Kubernetes matured and tried to solve this, and create an open source cloud native way with open standards for simplifying how we use clouds and how we basically see our infrastructures today to run our workloads and satisfy the technical and business requirements of multiple use cases to manage your overall infras. But if you talk about Kubernetes as a common control plane, I mean, Kubernetes has helped cloud for the future. I mean, for the today. And Kubernetes lets us use cloud services, infrastructures, our workloads, platforms, all locked in together. And of course, I mean, Kubernetes today, with all these cloud providers having their own Kubernetes in itself. I mean, GCP has GKE, or with Azure, you can use your AKS clusters. Kubernetes has turned platform equipped with services, different workloads, use cases, ability to use various applications together, simplifying IT operations and business requirements, and trying to enable cloud in an easier way. But that has given birth to the idea of platform engineering as a concept. And with platform engineering, developers today are focusing on building self-serviced internal platforms to basically make software delivery easier, enhance productivity, and ensure that operations and reliability as a concept, everything has come together to derive this overall concept of platform engineering, where it started as DevOps. And DevOps was developing where developers were just writing code, trying to deliver software. Delivery was not essentially at the right path, and that is what gave birth to the concept of platform engineering. And today, you are provided with automation, your infrastructure is becoming robust, your delivery is becoming easier with your CI/CD pipelines. So platform engineering is enabling DevOps and SRE practices at scale, and it's abstracting the complexities, and it's allowing developers to focus on code quality and ensure security, compliances, and efficiency. And that is where these kind of tools are coming up. You see Kubernetes developing, and so many other tools on container management, registry, policy making have come up. And implementation requires a better integrated developer portal, and that is what is being driven by these platform engineering practices. So before, as you know, before DevOps, application developers focused on writing code, as I said. But software delivery, why was it slow? Due to manual ticketing. Every process was manual. Each and every application required some sort of development, integration, framework, testing. And after the DevOps as a practice came in, software delivery sped up a lot. Like while the developer experience were suffering, and they were not wanting to learn about infra and all the cognitive overload and practices, and it was eventually causing lower productivity and developer burnout. But platform engineering emerged as a way to remove operational complexity and obviously ensured the benefits of DevOps staying in. So why was platform engineering considered? While organizations come and say, how do these relate to your organization, or why is platform engineering essential, the top reasons for considering platform engineering were obviously the agility, the cost, the reliability, and the consistency. So when you talk about agility, production releases happen only once in a month, and we want to accelerate our cloud journey. We want uh, i mean software to be agile, the releases to be robust, and a lot less of the bugs and the rig fixing, and lesser releases, patch fixes. So platform engineering enabled that. It helped clients, customers, reach that kind of a stage where production releases are more robust, and you don't need to focus more on the tests and fixes and all these things. And then you had more robust applications coming in to ensure reliability. One of the concepts you can say is the integration test that developed, the container registry, the management in itself developed, and that is where policy making. And beyond that, cloud native journey, with the amount of applications that are coming up, with the CNCF landscape that has been developing, we see that CNCF landscape is adding projects each and every day. Projects are maturing in their journey, and they are adding more code, they are adding more features and enhancements. So you know to continuously ensure that these features, these changes, these enhancements are being considered and are you know gelling in with the overall platform engineering you know was considered as something. And that is why we have seen the growth of the backstage or the Dapper project in itself. And moving on, from a manual standpoint, as you know, the more the manual processes, are incurred, the cost increases. We are wasting money, and the resources are being underutilized, and that actually has raised costs. I mean, it's not just, overutilizing cloud, but it is also about, ensuring that your cloud costs are managed, your manual tasks are reduced, and your tasks are automated. Even, I mean, there are multiple teams involved here. There is like an SRE team, there's a software delivery team, there's a QA team. So, for all these teams to come together and to be consistent in nature, platform engineering has helped, these teams collaborate in some sense. And again, reliability, as I spoke about initially, that we need to, I mean, there are so many critical incidents happening. There are so many outages. You see, there are, I mean, various companies out there, let's say the airlines companies, the e-commerce giants. There are so many outages, downtimes that are being caused, and it's too hard to, find out what has gone wrong, what are the tests that need to be done, or do we need to, focus on incident management practices, maybe use pager duty or fire hydrant. So again, I mean, platform engineering, which has enabled everything, all the applications are coming into one place. And software, as I said, you focus more and more on security. I mean, I think there are global practices which are different. There are so many policies brought up by the EU, or I mean, even in North America. I mean, there are continent specific, country specific. So again, these reasons, I mean, eventually ensure that considering platform engineering is the top goal right now. And last but not the least, consistency. I mean, it's too hard to manage different pipelines. I mean, you have to take care, your systems have to be consistent. So, and obviously we need to standardize these processes for security and compliance. So, and access controls, framework, standardized tooling. So of course that has somewhere led to the growth of platform engineering being adopted, and today we see a lot of platform engineering teams, platform engineers get their due in time. And if you talk about enterprise platforms, they need, I mean, developer self-service to obviously accelerate your app development with self-service provisioning of resources. There's requirement of operational simplicity. I mean, streamlining complex deployments across multiple clusters in multiple locations with different teams in consideration is very important. You need to obviously be able to customize these platforms. There has to be use case specific IDPs tailored to each application team, I mean, project or workload type, to maximize developer productivity, security, and compliance. You need to ensure, I mean, as I spoke about, the application and data are consistent across clusters and applications, and you're able to retain it. And then obviously the visibility and control, that is, you need to continuously monitor your metrics, you need to pull in your logs, you need to check in the costs, the performance of these deployments. So I mean, the enterprise way of doing it requires some amount of, metrics, compliances, and ensuring that your systems are stable, and there's, less of a downtime. And moving on, I mean, if you if you consider platform engineers, they need multi-cluster configurations. It's not easy. I mean, initially it was seen as one application being deployed on one cluster, but once the IDPs grew, and while creating IDPs, platform engineers need the ability to manage these multi-cluster configurations for a variety of use cases. I mean, there are AI ML use cases with generative AI growing beyond, I mean, what was imagined. And there's a stream, I mean, there's a requirement of managing these LLMs, having a streamlined management and process for the AI pipeline components and AI workloads for ML ops and AI ops. There's obviously a need to ensure that, you're able to manage these multi clusters in a robust way. And similarly, you have your hybrid multi clouds. Most enterprises are deploying workloads on both public clouds, on premise, and they need, a better way, a holistic way of managing this. So again, it proves the case for having better multi-cluster management provisions and configurations. There are edge and IoT cases, and fault tolerance needs to be improved by running workloads across clusters in multiple regions. You need to obviously maintain isolation, and these clusters need to be multi-tenant in nature, because there are multiple teams, they are working on different projects, they are sharing resources. And eventually, as I spoke about, different countries and state specific laws and clusters comply with laws that are specific to them. So there is a need to basically ensure that you are able to configure each cluster in a specific way. Moving on, obviously, while we have provisions such as the Kubernetes CAPI or the cluster API, or there are multiple tools out there, but there it also provides multiple challenges in itself. There are multiple challenges to multi-cluster platform engineering, and I mean, obviously it was seen as one of the best practices. It was seen was single app per cluster for workload isolation, as I spoke about. But most enterprises are adopting, as I said, hybrid multi-cloud, and need to deploy across multiple providers. For cost optimization, some organizations also use dynamic on-demand clusters, but with multi-cluster deployment, some challenges are Kubernetes sprawl, and inconsistent workloads and policies. There's a risk of non-compliance, and obviously the operational manual issues. Management complexities. They obviously make multi-cluster provisioning and multi-cluster platform engineering a challenge in itself. So, what are the options? What are the options we have with multi-cluster platform engineering? It isn't simple. Organizations face choices, and clearly you can't ignore this aspect. I mean, you need to prioritize absolute control and engineering, and there are multiple solutions. Either you do nothing, it's expensive in nature. Your infra teams, your ops teams, the costs keep growing. There are barriers to developer productivity. They have to manage that themselves. Teaming as a culture remains redundant, and it keeps going on. And you're not able to prioritize it. There's a DIY solution to it, which requires again a lot of specialized headcount, takes a lot of time, incurs risks. Now you're 100% responsible for platform resiliency, workload availability. So it's again complex in nature. There's a proprietary solution, which again, it can be expensive. There can be licensing issues. There can be limited integration options, where you might not be able to integrate it with your other platforms or other clusters. It can be hard. On premise and public cloud, the switching can be hard. And then eventually a solution where we are able to architect a complete Kubernetes native pure open source solution, where it's flexible in nature, it's integrated with the CNCF ecosystem, it's built on composability, and obviously you have your guardrails where you are able to maybe use feature flagging in some nature, and use certain features, not use them. And then obviously you curate all these components. You have version controlling, hardening, securing, and obviously making it available as and when required, which is enterprise native in nature, if that's the correct term to use. And that is where I would like to introduce k0rdent. k0rdent is the all new project. After fighting all the bigger hurdles of inconsistent cluster provisioning across cloud providers and on-premise setups, enters k0rdent, which is a Kubernetes native distributed container management environment. And it enables platform engineers to manage their infrastructures. It helps with cluster management for managing infrastructure, state management for your service catalogs, and obviously has a built-in observability feature as well. And there's an upcoming FinOps feature which ensures that there's cost control, you're ensuring stability in your environments, there's security, and your performance is also enhanced, and it's stable in nature. k0rdent obviously leverages a community driven approach to minimize your adoption risks. It acts as a super control plane, if I could say so. and it enables your centralized it enables your Kubernetes clusters to be managed in a centralized template driven way across your on-prem cloud or your hybrid environments. And by providing a repeatable, secure and standardized approach, obviously Cordant is helping you keep your IDPs composed and support modern and complex workloads, which are basically the truth today. And it has been obviously we have tested it as of now with AWS EC2, AWS EKS, Azure Compute, AKS, vSphere, OpenStack, and so far. And obviously there's a helm based templating system that makes it easier to standardize this approach and ensure reliability and compliance once again. So as I spoke about, I think I have covered a lot of what Cordant is and how Cordant looks like. The challenges it is addressing is managing clusters consistently across multiple environments, deploying and updating services across large fleet clusters. It maintains visibility and control as cluster counts grow into hundreds and thousands, and I think around 4,000, 5,000 clusters can also be managed using Cordant. I mean, obviously, I am waiting for Cordant to grow. It's just a project that has come up and has received positive community feedback. We'll also talk about the community in the end. But as I spoke about, the key design and principles are a templated approach, automated operations, unified management managed through a super control plane, and obviously it helps control your costs, and it provides a cost friendly approach. So all this I have covered. What is Cordant? What are the key benefits and how it helps? Kubernetes engineers, developers in today's world. And why Cordant? Obviously, as we spoke about, traditional Kubernetes has been inconsistent in nature. You need to configure each and every cluster. There are multiple teams involved, manual interventions. Increase the times and the costs, and there are operational bottlenecks when you scale your infrastructure, where more clusters are added, more applications are added to the platform layer. With Cordant, obviously there's a declarative way of managing clusters. The automated reconciliation assists removing the manual tasks. The multi-cloud and hybrid cloud support helps your cloud environments, no matter what kind of an environment you have, on-prem or cloud. And then obviously security and observability help you monitor and track the metrics and see what's happening in your systems, what is going wrong, if there's how do you need to scale them, how you are, if you are keeping in mind the policies or no. So with Cordant, all of this is also enabled. Lastly, why open source? That's the last topic I will cover. I think I don't need to define why open source software or why the open source way of doing it is the best way, but obviously you get in a community collaborated way of building your tool, building your project. You have a platform here where multiple users can come in. Already we are seeing folks diving deeper into Cordant, sharing their feedback. This is what they like, this is what they not like, creating issues, or maybe also looking to contribute to the project, which basically helps long term sustainability. Even in case, say, me or Bharat or anyone who's not able to contribute to the project in the near future or the longer future, we ensure that folks from the community are contributing to the project. Again, flexibility. As of now, as I said, Cordant is tested with these environments, but there are changing needs with AI and so many, cloud native technologies in itself growing. Open source ensures that there are multiple requests coming in and multiple things developing at the same time. So they make projects flexible, adaptive in nature, and obviously helps innovate faster, where development and deployment both in its core nature innovate and grow. And then obviously it empowers organizations to shape their future, gauge more control over their infrastructures. They are able to collaborate and integrate more open source tooling alongside. They help them run their POCs in a very faster way, and they have access to the tool at a broader way where they can also interact with their maintainers, maybe raise issues, solve them themselves, integrate it with other tooling to solve them. So the way, as Mirantis believes, is the open source way of doing it, and that is why Cordant today is open source in nature. So with this, I think I mean, as you know, this is the last slide I'll cover, and Bharat takes on from here. But this is just a way to, I mean, before we cover the architecture, this is just the way to ensure and show it to you how Cordant basically is accelerating time to value and reducing your manual activities and your costs. I mean, when you had to do it yourself, you had to deploy your Kubernetes, deploy your cluster APIs, deploy your providers, define your cluster YAMLs, which in itself was like so many lines of code. You need to, configure your providers, again deploy your clusters and your service templates. You need to deploy your monitoring applications tooling. Then you deploy a different tool for FinOps, say, a Cube Cost or a, I mean, I think there are so many other tools out there, your AWS cost centers, and then you need to operate them and manage your upgrades if there are multiple enhancements or more applications being added. And that was basically heavily burdening your ops. And there were many more steps you had to perform, many more components, and maintaining them became a hassle. But with Cordant, there are just a few steps. You deploy Cordant, you configure them, you deploy your clusters, you operate, and it, streamlines the management of your cluster and reduces the burden. So the value proposition of Cordant is, obviously, Cordant offers a comprehensive value proposition that addresses all these challenges which we spoke about initially. It makes your platform stable, it makes your platforms agile, there is efficient utilization of resources, there are, more savings, you are reducing your time to deploy. Even if you talk about your SRE practices, your SLO SLI management, there are lesser downtimes, and your mean time to recovery is faster. And obviously, with multi-cloud multi-cluster management being enabled by Cordant, you are reducing your risks, and obviously your critical incidents and non-compliances are also taken care of. So with this, I would allow Bharat to take over.
Thanks, Prithvi. That was quite a good introduction to Kotlin. I'll pick up where you left off. Basically, why the Kubernetes native approach, right? So a lot of people have tried to solve this cluster API problem, or look for an alternative with respect to cluster provisioning. And there are third-party tools out there, right? There's Crossplane, there's even Argo being used, there are a lot of other stuff. So why do we want to go the Kubernetes native approach and stick to the cluster API method, right? So like Prithvi said, we'll just look at the differences or rather how Kotlin complements cluster API. But before that, the reason to go the native way is because all the Kubernetes 6 projects and all the sub projects under it are heavily regulated and maintained, and appreciated upstream, right? So third-party tool might have a particular way of doing things that might not be the industry standard. And you're obviously stuck to the way that they are doing things. But by following the Kubernetes native upstream approach, we maintain with the flow and the development cycles of upstream Kubernetes and all the various components that usually make up a cluster. Invariably, the productivity and optimization increases for both the platform engineers as well as the developers. One side, there's reduced complexity for the platform engineers in order to maintain the clusters, do the clusters, and um, scale the clusters and all these things. And on the other side, there's very easy, simple way for developers to request a cluster for their own use, for teams to request clusters. So usually what we call as a self-service platform is what one of the main goals of Cordant is, and it's made really optimal for that particular use case. why CAPI is something I talked about, and how does it differ, right? Because when you look at a little bit of the technical side of the project, we are using pretty much the same downstream components of CAPI. So what are the differences if someone wants to understand when they're introduced to Kotlin? With CAPI, there's a lot of manual steps that you have to do if you want to provision a cluster, right? Anyone who's worked with CAPI knows this. And these manual steps are not the same for different cloud providers. So with each cloud provider, there's a different set of things that you have to follow. And it has its own complexities and instructions that comes with it. So what we've done in Quadrant is take away all these complexities and give you a simple CR that you have to work with called as cluster deployment, which we'll look into later, and define all your cluster configuration in just that single CR. And these CRs are also readily available in our documentation as well. All you need to actually do is just work with setting the configuration for your cluster deployment resource, right? We'll see how that looks like. And that's about the first step in order to provision clusters, right? And with CAPI, there's also another layer of complexity. We have to work with multiple infrastructure providers, which I mentioned already. It changes based on the cloud provider that you'll choose, right? So that is also handled, quite smoothly in Kotlin. Then there's the challenge of day two, right? So let's say you do have your cluster up and running. Pretty much every team in every company needs certain things installed on top of a bare minimum cluster. Let's say Cert Manager or Istio, right, or Vault or any of these tools that's commonly used, right? So Cordant also handles this by using something called as the service templates. So there's cluster templates for cluster management and service templates for application management, right? So for application management, like the apps that I mentioned, you define your service template and then specify that in the cluster deployment. It's easy as that. So the application that you want is automatically deployed onto the cluster once the cluster is provisioned. And this can be scaled up quite easily, which is always a pain, right? Even if you do have a script or an automated solution to do this, for example, install Vault on your 27 different clusters, right? You still need to do it individually for 27 clusters. But with this, you just need to mention the configuration at one place, and then that's propagated to all your clusters, right? So the last but not the least is the observability stack, which Prithvi has mentioned quite a few times. Again, this is a huge market in Kubernetes, and there are a lot of players, right? But having to deal with observability across multiple clusters, where we call the management clusters as the mothership cluster and the workload clusters as the child clusters, right, is going to be extremely complex and equally important. And that's why we have an inbuilt observability tool called a SCOF that comes with Kotlin. So now let's look at the architecture. Primarily, like I said, there are three components, the third one being COF, which is for observability, and these two, which is the cluster manager and the service manager. So KCM, cluster manager, is for orchestrating your CAPI or CAPEX controllers, right? So all the different infrastructure providers are basically handled with this KCM controller, right? This would handle requests that are coming in from the user, translates them, and then interacts with the other CAPEX controllers, and then make sure the cluster is provisioned until the end. KSM, which is a service manager, is the other controller that's in Cordant for application management. So the applications that I mentioned are handled and reconciled using this controller. So we use Sweltos under the hood to take care of this, right? And as you can see in the box up here, the primary resource, like I mentioned, is the cluster deployment, which uses a cluster template. And there is a service template, which again is referenced in the cluster deployment. IDPs, internal developer platforms, have a lot of components, right? And to come up with an efficient, scalable IDP will take a lot of effort across tools. So as you can see in the bottom right here, there's the cluster composition and management tools, right? So there's Linkerd, Infra, Dapper, and so many similar tools, Crossplane and others, that you'll have to work with, understand how they're doing it, and follow the templates and rules and compositions that they have. And then you'll have the observability stack. Again, so Fluentd, Yager, OpenTelemetry, Prometheus, Grafana, Elastic, all these are there, right? These would be individually installed, configured, and then scaled up, maintained, and so on. That becomes again an additional overhead, which is avoided here with k0rdent because this comes baked into the stack. Then there's services, right? So service catalog, like I said, you can pretty much use any tool that's for continuous deployment or automating via script or anything like that. But we use Sveltos under the hood with k0rdent State Manager. And then at the top layer, you have the user interactions and user applications running, which could belong to pretty much any category in anything that's in your business use case, right? We already looked at this. Right. So a question that we've heard frequently is how does k0rdent templates really differ that much from cluster class? After all, cluster class is also a repeatable, configurable, CR that can be done once and then reused, right? Well, yes, but not really, right? If you actually look at it closely, at an overview, you can define rules and then you can define a template and keep it in a cluster class. But then the day-to-day operations which are required, such as in-place upgrades or choices of the services, version controls, and approval processes, all these things are severely limited in a cluster class. Whereas in k0rdent templates, it's quite flexible to handle all these things. So let's now look at a demo. So let's jump directly into how do we get started with k0rdent. All you need is a management cluster, and a management cluster can be as simple as a kind cluster, or it could be running on any of your cloud infrastructures, anything at all, right? So once you have a management cluster and you have the prerequisites covered, installing k0rdent is as simple as doing a Helm install of our package, right? So doing a Helm install will basically pull in all the components that are part of k0rdent, including the CapEx controllers, which I've talked about, and then be ready in order to take the cluster deployments and other CRs of k0rdent, right? So as the guide says, you can pretty much follow this guide and then make sure that everything is ready. And I'm going to show you that in real time. So I already have k0rdent installed on my kind cluster. We'll just verify that everything is running fine, right? So kubectl-m KCM system is what I've set the alias for KA, just as a disclaimer. We have all these infrastructure dependent controllers, CAPI for AWS, the upstream CAPI, OpenStack, vSphere, and Azure. Then we have the Cosmotron controllers as well, which basically acts as the controller for managing or installing the control planes on the workload clusters. Then we have a bunch of other KCM related controllers and other deployments, right? The next thing we'll have to verify is look at all our cluster templates. So when you install KCM, it comes pre-installed with a list of cluster templates for different providers. As you can see, there's a bunch for AWS, there's a bunch for Azure and vSphere and OpenStack as well. Then there is service templates, which, like I said, is application specific, right? So you can see DEX, external secrets, GPU for, it's part of NVIDIA, Ingress Nginx, and so on. Now, in the interest of time, and since this is really an introduction, I will show you the cluster deployments that are already on the cluster. So I've got one on OpenStack and two on Azure. I've got in two different regions, Central India and then South India. And this is running on our internal use stack. So this is our private cloud and this is our public cloud. The definition that's required in order to boot this up is this. So if I do this, right, this is how you specify services. So right now, I have deployed the GPU operator once the cluster is provisioned. But this is where you mention the template. So these are the key components that I'm trying to highlight. In your cluster deployment, you have to specify the template based on the cloud. You have to specify the credential, which helps interacting with the set cloud. And then you mention your particular configuration, right? So the control plane has the standard A4V2, which is typically a CPU-based VM. But the worker node, since I wanted to run AI workloads, has a GPU-enabled node. So this has testability for NVIDIA GPUs, right? And these things are, again, infrastructure-specific configuration that would change based on the infrastructure. So for Azure, it expects tenant ID, client ID, secret. Whereas for OpenStack, it expects a different bunch of things, and so on for AWS and vSphere as well. So these instructions are provided in the docs on how to configure the secret, and then configure the secret on your Kubernetes cluster, the management cluster, as well as on your Azure portal. Just a quick note, the secret ultimately is not referenced directly. We have a CR called as credential, which references the cluster identity of Azure, and then that points to the secret, right? So no secret, the direct secret with the credentials is not directly exposed to any of the developers or any of your users who are actually using the cluster, right? Now, let's see another. Yeah, now let's actually export the kubeconfig, which lives as a secret in the same namespace, right? So I'm going to export this and then just open a new tab, do that, and I'm in my OpenStack, right? So if you see, I've used one worker node and one control plane. This is for Azure, but I've essentially used a similar configuration for OpenStack as well. And there you go. So there's the control plane, and then there's the worker node, right? Similarly, let's log into Azure, which I've already exported here, right? And then as you can see, this particular namespace and all the resources in it were deployed because we had specified the service template. So it's as simple as this. You have your cluster deployment, defines your cluster configuration, and a cluster is provisioned. And in the cluster deployment, you specify your services, and then the Sweltos component that's underneath takes care of provisioning that particular component. So this whole process, which used to be manually painful, is now pretty much streamlined and quite convenient. So that's pretty much it as a brief introduction to k0rdent. I would like to ask everyone to explore the documentation because we have a whole bunch of stuff there. And then there's obviously the KCM repository where the main development in all the components of KCM is happening. And it's completely open source. You can check out all the providers that are being supported right now. And if you wish to add a provider, you can definitely create an issue and discuss it in the community calls. And then we can work on that.
So with this, I hope folks can hear me. With this, we are
Yeah, yeah,
on
we can.
the end of the webinar. There was a lot of learnings here. People can get started with Cordant. Maybe we'll obviously share the links to the docs and getting started with Cordant, the GitHub. But as you mentioned, I mean, Cordant, it helps achieve your platform engineering goals. It has a declarative template sort of an approach, and it allows you to consistently ensure smooth multi-cluster operations. It obviously provides you with a powerful automation tool to streamline your platform engineering workflows, make ensure that you're following the right purpose, the right security, and the compliances. And I mean, it's very easy to get started with Cordant. You can pull in a Helm chart, it's just a couple of lines, or you can go to the Kubernetes native way. And once you're getting started, you manage your clusters, use the, I mean, management cluster to manage your child clusters, as I think Bharat gave us a demo. And there will obviously be more happening with Cordant. The community will develop. We'll see a lot more releases coming up, and a lot more features, a lot more enterprise native approach coming in, and Cordant developing. But for now, as next steps, ensure that you're joining the Cordant community. Scan this QR to join the CNCF workspace. Join the hashtag Cordant channel on the CNCF Slack. And once you're part of it, drop in your feedback, drop in your questions, join the community calls, ask us any questions you have on Cordant, and make sure you're supporting Cordant by dropping in a star for the project as it's pretty new and nascent. And ensure you're following the socials for more updates on Cordant by us or the Mirantis team. So with this, we would like to wrap up the webinar today. And if there are any questions, Bharat and me are happy to take them. But thank you so much, everyone who has tuned in or who will watch it later on demand. Thank you so much once again for supporting it. And thank you so much, Grace and Juni from the marketing team, too.
Thanks, folks. It's a good opportunity to introduce Kotlin to the community. And it's a new project. It's a growing project, but I think it solves a very painful and important problem in the Kubernetes provisioning world, in the platform engineering world. And yeah, looking forward to see the project grow.